Okay. X is Hausdorff if and only if the diagonal is closed in the product topology. Okay. Well, let's assume that. Let's go this way and assume that the diagonal is closed. So that means x cross x minus the diagonal is open. And so let x1 and x2 be elements of x which are different. Okay, I guess we have to start off by assuming that the set has more than one element, otherwise this is kind of trivial. So since it's open, there's some basis element u1 cross u2 that contains x1 cross x2 and is contained within the complement of the diagonal, just because it's an open set. So xi is where xi is an element of ui's. Now, we want the ui's to be our neighborhood, so we want u1 intersect u2 to be empty. And that's true because otherwise we'd have a y cross y, an element of u1 cross u2, but that's in the diagonal, and u1 cross u2 is definitely defined not to be in the diagonal. So we have x is Hausdorff. Okay, what about going the other way? Let's say we're Hausdorff, so let's say x is Hausdorff. Y is the diagonal closed. So we have x1, x2. Let's say that's in the complement of the diagonal. So that means x1 is not equal to x2. So since it's Hausdorff, there exists, this is basically the other proof going the other way. We have u1, u2 open with with their intersection being empty. And we've got x1 cross x2 in u1 cross u2. So this, we claim this open set is contained within x1 cross x2 minus the diagonal, because otherwise we'd have a y, right? If it wasn't, if it intersected with the diagonal, that means there'd be a y that lied in y1 and a y in u2. So y cross y would be in u1, u2, and this would contradict the fact that the sets are disjoint. So any element of the complement can be put inside an open set. So therefore, x cross x minus the diagonal is open. So that means the diagonal is closed. Okay, this is probably the longest problem of the assignment because it had 4 little parts. So let's do part A. We've got to show that it's disjoint. So if x is in the boundary of A, which we define to be the intersection between the closure of A and the closure of the complement of A. So that means x is in both the closure of A and in the closure of the complement. So every neighborhood of X intersects the complement of A. So no neighborhood of X lies entirely in A. So X can't be in the interior of A. So that shows us that the interior and the boundary are disjoint. And if X is in the closure of A subtracted the interior of A, then every neighborhood of X intersects X minus A, and so X is in the boundary of A. And so A prime then is going to be interior of A union the boundary of A. And that gives us part A. In part B, if the boundary of A is empty, then the closure of A equals the interior of A, but we have that the interior of A is contained within A, is contained within that closure of A. So that means if that's true, then the closure of A equals the interior of A, then all these things are open, are equalities. And then this shows that A is the interior of A, so it's open, and A is equal to the closure of A, so it's closed. And if A is open and closed, then A equals the interior of A because it's open. So the closure of A is equal to the interior of A union its boundary. But the interior of A equals A. And if A is closed, then A is equal to A union the boundary of A. But the interior of A and the boundary of A are disjoint. So A intersected boundary of A is going to be empty. So that means the boundary of A has to be empty. And continue on to part C. If U is open, then the closure of U equals the interior of U union with the boundary of U. So the closure of U minus the interior of U has to equal the boundary of U because the boundary and the interior are disjoint. So U prime minus U, because U is open, is equal to the boundary of U. What happens the other way? What happens if U, closure of U minus U equals the boundary of U? Well, the interior of U intersected union the boundary of U minus U equals the boundary of U. So U, conclude from that U equals the interior of U, so U is open. And then finally for part D, well, the answer to that is definitely no. For example, if U equals Q, right, then the interior, the closure of Q is R, and the interior of R is R. So we haven't got our set back to where we started from.